We are counting down the 10 Soviet inventions that tried to bend, twist, or smash the laws of physics, and they paid the price. From land machines that sank into the mud, to ships that spun in circles, to planes so ambitious they barely left the ground, each entry faced the same fate: brute force design colliding with the hard limits of nature. These are not just tales of broken metal, they are case studies in how raw ambition and political pressure birthed some of history's most spectacular engineering failures. Which impossible project left the biggest crater? Let's start at number 10. Imagine a tricycle towering 40 feet tall, weighing 60 tons, with front wheels as big as Ferris wheels, 9 meters across. That was the Tsar tank, built in 1915 to roll over forests and trenches like they were nothing. But all that weight pressed down on a single tiny rear wheel just 1.5 meters wide. The front wheels barely dented the ground, but the rear crushed the soil with 15 kilograms per square centimeter, far beyond what the Earth could hold. The result was that it traveled barely 200 yards before sinking into the mud. The Tsar tank sat abandoned for 7 years, a monument to brute force losing to ground pressure before being scrapped in 1923. 12 meters long and armored like a submarine, the ZIL 2906 crawled across Siberia on a pair of spinning Archimedes screws, each nearly 2 meters in diameter. In the swamps, it was unstoppable, gliding at 10 kilometers per hour where tanks and trucks would drown. But the moment it touched hard ground, friction turned those screws into grinders. On concrete, the steel augers chewed themselves to pieces and left craters in their wake. The machine could go anywhere, just not anywhere with a road. Only 2 were built, and one still survives in a Russian museum, a relic of the battle between Soviet ambition and the laws of abrasion. In 1971, Soviet engineers mounted 2 Yak-40 jet engines on a commuter railcar and sent it hurtling down the tracks at 160 kilometers per hour, sometimes pushing 250. The SVL turbojet train was supposed to break speed records and prove Soviet rail could rival the West, but jet thrust on steel rails brought its own problems. The engines burned 1,000 liters of fuel per kilometer, turning every trip into a bonfire of kerosene. During tests, ballast stones and debris were sucked into the intakes, bending fan blades and threatening to pull in anything nearby. The SVL could outrun adhesion limits, but not economics or basic safety. After just a few trials, the project was shelved and Soviet rail returned to electrification. A warship shaped like a dinner plate, 31 meters across, drifting on the Black Sea. This was the Novgorod. Designed in the 1870s and still studied by Soviet naval engineers as a case study in brute force optimism, it was supposed to be the ultimate stable gun platform. The idea was simple: a circular hull would resist rolling, letting 2 cannons with a caliber of 279 millimeters blast away no matter the waves. But physics had other plans. Ships are long for a reason. They slice through water to minimize resistance. The Novgorod's round hull had a drag coefficient of 1.2, nearly 6 times higher than a typical warship. It crawled at barely 6 knots, engines straining just to push it forward. The real disaster struck when the guns fired. Each broadside spun the entire ship on its axis, sometimes rotating 180 degrees before the crew could react. Gunners lost their bearings, and officers reported seasickness from the endless spinning. In calm water, the Novgorod was a sluggish target. In battle, it became a floating carousel. The ship was quietly retired and scrapped after less than a decade. It was a perfect lesson in what happens when hydrodynamics is treated as an afterthought. In 1969, Soviet shipyards in the closed city of Severodvinsk launched something the West had never seen: a submarine built entirely from titanium. The K-222, known to NATO as Papa Class and to Soviet sailors as the Golden Fish, weighed 2,400 tons and cost so much that even Gosplan accountants joked it should be measured in gold, not rubles. The ambition was simple: create a machine fast enough to outrun any torpedo in the NATO arsenal. During sea trials, K-222 shattered records, reaching 44.7 knots submerged, over 50 miles per hour underwater. At that speed, it was less a submarine and more a bullet tearing through the sea. But physics had its own price list. When a propeller spins fast enough, it creates cavitation, tiny vapor bubbles that collapse with the force of a small explosion. At over 40 knots, the K-222's propellers carved a trail of collapsing bubbles, battering the hull with shockwaves reaching 1,000 atmospheres. The titanium plating, 8 centimeters thick, began to erode. Inside, the noise was deafening. Acoustic logs recorded sound levels over 100 decibels, loud enough to drown out sonar and leave the crew nearly blind underwater. NATO submarines did not have to chase the golden fish. They could hear it coming from miles away. The K-222 was a technical marvel, but it was tactically useless. It could outrun a torpedo, but not its own echo. By the late 1970s, the submarine was quietly retired. The speed record still stands, but the lesson was clear. You cannot cheat cavitation. The faster you go, the louder and more vulnerable you become. 52 meters from wingtip to wingtip, the Kalinin K-7 was a flying fortress built in secret in Kharkiv. 7 engines lined its thick, stubby wings. Machine gun turrets sat in the landing gear, but the real enemy was hidden in the structure itself. When those 7 propellers spun up, their vibrations matched the natural frequency of the tail booms, about 12 Hz. Engineers warned about resonance, but the Politburo wanted results, not more tests. On its 7th flight, the oscillations grew violent. The tail tore away in mid-air. The K-7 plunged into the ground, taking 14 lives with it, including the chief test pilot. The fatal flaw was resonance. When the rhythm of the engines matched the airframe's own heartbeat, the structure shook itself to pieces. The K-7's wreckage was quietly cleared away, but the lesson was written into every future Soviet bomber: ignore natural frequency, and the sky will tear your machine apart. Robert Bartini spent decades sketching dreams of machines that could leap from water to sky, hunt submarines, and outmaneuver any NATO fleet. In 1972, his vision took shape as the VVA-14, a bulbous amphibious aircraft with the wingspan of a jetliner and the body of a turtle. The plan was radical. Vertical takeoff from the sea, cruising just above the waves in ground effect, then climbing to altitude like a conventional plane. 6 lift jets were supposed to provide the vertical thrust, but the engines never arrived. The Ministry of Aviation redirected them to the MiG-25 program, a higher military priority. Bartini's correspondence from the era is filled with frustration. He called it a machine without a heart. With no lift jets, the VVA-14 could only take off like a lumbering seaplane. Engineers bolted on inflatable pontoons just to keep it afloat. The hybrid design struggled with drag in the water and instability in the air. It was too heavy to hover, too awkward to fly efficiently, and too delicate to handle rough seas. The VVA-14 was left stranded between 2 worlds, a compromise that satisfied neither hydrodynamics nor aerodynamics. Only 2 prototypes were built, both left to rot at the Monino Museum outside Moscow. The fatal flaw was clear. In trying to master every domain, the VVA-14 failed to conquer even one. Its rusting hulk is all that remains, a silent witness to the cost of ambition undone by politics and physics alike. In 1987, the Soviet Navy unveiled the Lund-class Ekranoplan, a machine that looked like a cross between a cargo jet, a missile cruiser, and a beached whale. 74 meters long, with a wingspan wider than a Boeing 747 and powered by 8 NK-87 turbofans, the Lund was designed to skim 5 to 10 meters above the Caspian Sea, carrying 6 P-270 Moskit anti-ship missiles on its back. The plan was simple on paper: use ground effect to fly under radar, deliver a missile barrage at 500 kilometers per hour, and vanish before NATO could react. But the laws of physics had other ideas. Ground effect is a fleeting gift. When a wing flies close to a surface, within 1/10 to 1/3 of its span, it rides on a cushion of high-pressure air, cutting drag nearly in half and boosting lift. The catch: the effect is strongest and most unstable at extremely low altitudes. For the Lund, That meant flying in a razor-thin vertical band just 4 to 12 meters above the water. Drop too low and a wave could rip off a wing. Climb too high and the magic vanished, leaving 544 tons of steel with nowhere to go but down. Every wave was a threat. In calm seas, the Lun could cruise for hundreds of kilometers, but as soon as wave heights topped 2 meters, the ride turned violent. The nose would pitch up over a crest, shifting the center of pressure and sending the whole craft into a porpoising motion, oscillating up and down and risking a catastrophic stall or a nose-first dive into the sea. Pilots described the workload as relentless, constantly fighting to keep the craft in its narrow safety envelope. Turning was no easier. Bank too far and the low wingtip could strike the water. Even a gentle turn required a radius of several hundred meters, making the Lun behave more like a ship than a plane. The concept was born in secrecy. Rostislav Alexeyev, the chief designer, worked from a closed facility near Nizhny Novgorod, his diaries filled with calculations and mounting frustration. The Politburo demanded a weapon that could outpace Western navies, and the Caspian Sea became the test site for this new breed of war machine. Western analysts first spotted the prototype, nicknamed the Caspian Sea Monster, in 1967, when a KH-4 spy satellite snapped an image of an enormous shadow gliding just above the water. The CIA filed it under unidentified, but soon realized it was neither a boat nor a plane. It was something in between, and it terrified them until they learned its secret. The fatal flaw was the ground itself. The Lun was a prisoner of the 1/10 to 1/3 of its wingspan altitude band. Outside of that band, it was either a brick or a target. In rough seas, it was forced to stay docked. In combat, its massive radar signature and limited maneuverability made it easy prey for modern missiles. The Navy quietly cancelled further production after just one was built. Alexeyev's health declined, and he died in 1980 before seeing his creation sidelined. The Lun's hulking frame now sits abandoned on a Caspian beach, a monument to brute force ambition and the unforgiving precision of ground effect physics. The lesson was clear. You can scale up engines and steel, but you cannot scale up the laws of aerodynamics. Even the most monstrous machines are still at the mercy of the waves. In the Ural mining fields, Soviet engineers set out to build machines that could move mountains, literally. The walking excavator was their answer, a colossus that did not roll or crawl, but strode across the earth on hydraulic feet. The largest prototypes weighed hundreds of tons, with each step pressing down on the ground like a building coming to life. The theory was elegant: spread the weight over massive shoes, keep ground pressure low, and the machine could walk where tracks would sink. But as these giants grew, the numbers turned against them. Every time you double a machine's size, its mass increases 8 times, while the area of its feet only increases 4 times. That is the square-cube law in action. Uralmash data from the 1970s showed ground contact pressures climbing toward 500 kilopascals, 5 times what soft soil could support. In the end, the biggest walkers did not conquer the earth, they burdened it. Some had to be dismantled where they stood, unable to move without crushing the very ground they were meant to mine. The fatal flaw was not bad engineering, it was physics. No matter how much steel you add, you cannot scale your way out of the laws of nature. At the edge of the Kazakh steppe, behind barbed wire and armed patrols, Soviet engineers assembled something the world had never seen. A lunar rocket standing 105 meters tall and bristling with 30 engines at its base. The N-1 was the answer to the Saturn V, a machine built not by choice, but by necessity. Soviet industry could not produce a single giant engine like the Americans, so they clustered 30 NK-15s, each smaller and more temperamental, hoping that together they could brute force a path to the moon. Inside Block A, the first stage, fuel and oxidizer raced through a maze of pipes and manifolds. The plumbing alone weighed more than a destroyer. Every launch was a gamble. 30 engines meant 30 times the risk of leaks, surges, and vibration. The KORD control system watched over them, but with sensors sampling every second or two, it was always a step behind the chaos. On February 21st, 1969, the first N1 stood ready. At ignition, the clustered engines roared to life, shaking the pad with 4,500 tons of thrust. Seconds later, a voltage spike triggered cord to shut down two engines. Pogo oscillations, pressure waves racing up and down the fuel lines, set off a chain reaction. A leak turned into a fire. Within a minute, electrical shorts and hydraulic failures forced a full shutdown. The rocket crashed just beyond the pad, a smoking crater where the world's largest launch vehicle had stood. The second attempt, July 3, 1969, was worse. 10 seconds after liftoff, a roll began at the base. Eddies in the exhaust plumes twisted the rocket. KORD, tuned to be more cautious after the first disaster, shut down nearly all the engines at once. The N1 toppled back onto the pad, and the resulting explosion equaled nearly a kiloton of TNT, by far the largest non-nuclear blast in history. The shockwave shattered windows 40 kilometers away. Baikonur's pad was vaporized, but the site had been evacuated. No one died, but the Soviet lunar dream was buried under concrete and twisted steel. Two more launches followed in 1971 and 1972. Each time the rocket failed before reaching space. One broke up as uncontrolled roll exceeded the steering engine's limits. Another suffered a hydraulic shock, water hammer from a sudden engine shutdown, bursting core lines and detonating a turbopump. Engineers pored over missions memos and telemetry, tracing failures to pressure spikes, resonance, and the impossibility of managing 30 engines with analog controls. The Americans tested the Saturn V's 5 engines together over and over before risking a flight. The Soviets, under Politburo deadlines and budget cuts, never static, fired the full N1 cluster. Every launch was a first test. Every failure was classified. By 1974, after 4 catastrophic losses, the program was cancelled. The N1 had cost billions of rubles, but never flew a single mission. Its legacy is a crater at Baikonur, a pile of blueprints, and the lesson that you cannot outvote the laws of physics. The largest machine ever built for the moon was defeated not by the Americans, but by the physics of plumbing, vibration, and time. Across all 10 Soviet megaprojects, one pattern stands out. Brute force cannot outvote physics. When ideology demanded the impossible, reality pushed back, with mud, vibration, and fire. These failed leviathans remind us that ambition is vital, but nature always gets the final say. In engineering, as in history, the laws of physics are the only laws that never change. Thanks for watching. Let us know which experiment amazed you most.